Imagine you have a million names to sort alphabetically. How do you do it? You could go through the list again and again, swapping adjacent names that are out of order. That is bubble sort. It works. But it is also one of the slowest algorithms ever invented. Sorting is one of the most studied problems in all of computer science, and the solutions reveal something profound about how we think about time and efficiency. Before we sort, we need a way to measure how good an algorithm is. Big O notation describes how an algorithm scales as input grows. O of n squared means if you double the data, the work quadruples. O of n log n means it grows much more slowly. The difference matters enormously at scale. Sorting a million items with O of n squared takes a trillion operations. With O of n log n, it takes just 20 million. Bubble sort repeatedly steps through the list, compares adjacent elements, and swaps them. Selection sort finds the smallest element and puts it first, then finds the next smallest, and so on. Insertion sort builds the sorted list one item at a time, like sorting a hand of cards. All three are O of n squared. Fine for small lists. Catastrophic for large ones. Merge sort uses divide and conquer. Split the list in half. Sort each half. Merge them back together. The merge step is O of n. You do it at log n levels of recursion. Total. O of n log n. It is fast. It is stable. And it is predictable. The catch? It needs extra memory. A copy of the array to merge into. That is the trade-off. Quicksort picks a pivot element and partitions the array. Everything smaller goes left. Everything larger goes right. Then it recurses on both halves. Average case. O of n log n. Worst case. O of n squared. But this almost never happens with good pivot selection. In practice, quicksort is often the fastest sorting algorithm in the real world because of cache efficiency. Heap sort uses a data structure called a binary heap. It first builds a max heap from the array. This takes O of n, then it repeatedly extracts the maximum element and places it at the end. Each extraction is O of log n total. O of n log n heap sort is in place and has consistent performance. But it is not cache friendly, making it slower than quicksort in practice. Not all sorting is comparison based. Counting sort works by counting how many times each value appears, then reconstructing the sorted list. It is O of n plus k, where k is the range of values. Radix sort sorts digit by digit. Bucket sort distributes items into buckets, then sorts each bucket. These can beat O of n log n, but only under specific conditions. There is no universal winner. Python's built-in sort uses timsort, a hybrid of merge sort and insertion sort that exploits naturally ordered runs in real data. Java's array sort uses dual pivot quicksort for primitives and timsort for objects. Sorting is solved. Use your language's built-in. But understanding how these algorithms work makes you a fundamentally better programmer, because the same ideas appear everywhere in computer science.